sklearnensembleStackingClassifier Stacking Classifier. Description: the stacking classifier is a powerful ensemble method in scikit-learn that combines multiple Bayes estimators classifiers to create a more robust and accurate prediction model. It works by training individual Bayes models on the original dataset and then training a final meta estimator on the predictions from the Bayes models. This process leverages the strengths of different models and helps to mitigate weaknesses, leading to improved generalization performance. Inputs: Bayes estimators list a list of Bayes classifiers that will be trained on the original dataset. Each Bayes estimator should be an instance of a scikit-learn classifier class, e.g. logistic regression, random forest classifier, gradient boosting classifier, etc. Final estimator, a scikit-learn classifier that will be trained on the predictions of the Bayes estimators. This meta estimator combines the outputs of the Bayes models to make the final prediction. Outputs: predictions, the predicted class labels for new data points. Probability is optional if the final estimator supports probability estimation. It will also return the probability of each class for each data point. Steps: training. Each Bayes estimator is trained independently on the original dataset. The predictions made by each Bayes estimator are collected. Meta estimator training. The final estimator is trained using the predictions from the Bayes estimators as features. Metrics. Accuracy measures the proportion of correctly classified instances. Precision measures the proportion of true positives among all positive predictions. Recall measures the proportion of true positives among all actual positive instances. F1 score, the harmonic mean of precision and recall. Visualization plots. Feature importance plots the relative importance of each Bayes estimator's predictions in the final model. Confusion matrix visualizes the classification performance, showing the number of true positives, false positives, true negatives, and false negatives. Fine-tune parameters. Bayes estimators experiment with different Bayes classifiers and their hyperparameters to find the best combination. Final estimator: choose a final estimator that is suitable for the specific task and adjust its hyperparameters accordingly. Stacking parameters adjust the CV cross-validation folds and pass-through parameters to control the stacking process. Uncertainty methods. Confidence scores use the probability estimates provided by the final estimator to assess the uncertainty of predictions. Ensemble variance calculate the variance of predictions across the Bayes estimators to estimate uncertainty. Challenges and fixes. Challenge 1: overfitting to Bayes estimator predictions. Sample use case: a stacking model might overfit to the predictions of a single strong Bayes estimator, leading to poor generalization on unseen data. Fixes. Use cross-validation during meta estimator training to prevent overfitting. Regularize the final estimator to reduce its complexity. Experiment with different Bayes estimators and their hyperparameters. Challenge 2: high computational cost. Sample use case stacking can be computationally expensive, especially with a large number of Bayes estimators or a large dataset. Fixes. Reduce the number of Bayes estimators or simplify their models. Use efficient algorithms for meta estimator training. Optimize code for parallel processing or distributed computing.